Okay, let's go ahead and get started. Welcome everybody to our second of these Zoom webinar type of meetings. Talk a little bit about Green Bank Observatory and the GBT and what's going on with it. I'm Karen O'Neill. I am the director of Green Bank Observatory. I will be starting this off. A couple weeks ago, we had an overview session talking about where we were with the observatory and also talking about some of the new instrumentation with our pulsar work. And so today, again, I'll give a very brief update just on Green Bank Observatory itself, where we are with it. And then we're going to focus more on the high frequency end of things. So once I'm done, I'll hand off the discussion to Dave Frayer, who will talk a lot about the spectroscopy and future instrumentation there. And then after that, Pedro Salas will be talking about Lassi, a new laser active scanning surface instrument that we have. A couple notes, since this is a Zoom meeting. First off, please be aware that we are recording this meeting. This is so that anybody who wasn't able to attend it today will be able to go back and see the status of the observatory. Second thing to note is if you do have any questions to keep things flowing here, please just use the chat window for those, and we'll read your questions out and go ahead and answer them. So with that, let me just go ahead and start going through a brief status update of Green Bank Observatory. So first off, looking at the bigger picture, the state of West Virginia. West Virginia is beginning to ease its restrictions as a result of COVID-19. The plan is to continue to slowly ease these restrictions for as long as the percentage of positive cases within the state remains below 3%. So today it's about 2.3%, for example. This is a very gradual startup, looking at initially small businesses and other limited activities that can start to open up, and then looking across the next many weeks to slowly try to reduce the restrictions over time to allow more and more to open. Having said that, Green Bank Observatory is operating and continues to operate as an essential business within the state. That means that we have a skeleton crew on site, and following safe practices, the majority of our staff are working at home. So what does that actually look like? It means we have telescope operators in 24 hours a day, 7 days a week to keep the GBT up and running. And then we have scheduled maintenance crews that come in and work as a group to keep the operations continuous. Overall, things have gone incredibly well for the Green Bank Observatory and the GBT since March 8th when we first started this process. We did have some downtime in mid-April due to power outages and storms, but even with all of the complications involved with the current pandemic, staff were able to get the GBT back up and running again within 5 days, which was phenomenal. Other things are running on schedule, so proposal reviews have happened. We had the director's review of proposals just today, and we anticipate a release of the dispositions for the 20B semester in mid-May, so around the 15th of May, and those are directly on track. Other exciting news for Green Bank Observatory is that this week we finally did our first receiver changes. So the X-band refrigerator has been down since mid-March, and yesterday a crew went in and swapped the refrigerator out, and it's cooling down now and it should be usable. And today the KA band receiver and the CCB were installed up on the telescope, and we'll be checking that out tonight. So bits of progress, and it's exciting to start to see these new instruments coming on board. The staff have really been working hard to find ways to do this and make it safe while still maximizing the science we can get out of the telescope. Equally as exciting, we are also beginning a little bit of work within our machine shop and other shop areas. And so at the moment, it's just 2 people at a time working on the receiver systems. But we are going to move forward on that. So we've got the ultra wideband feed in the shop right now, and some work going on with that to help it move forward. And then soon after that, we're hoping to work on the Lassi feed. Looking at the other things going on, all of our educational programs currently are only remote. The Science Center is shut down. We don't have any tours going. And additionally, we don't have any visitors on site. So this isn't just educational visitors. This is all observers and everything else. Currently, all of the camps, the workshops, and so forth that were scheduled through June are canceled or postponed. This includes the single dish school that was originally scheduled for the spring has now been rescheduled to October. We have a spring training workshop that has been canceled, although our fall one is still on the schedule. The OSMA at 60 workshop that was scheduled for the end of April is being rescheduled. The dates have not been finalized yet, but it could be in April. And finally, we do have an Argos 144 workshop, which Dave Frayer will be talking about, that is scheduled for the fall. So that's not delayed. That was actually scheduled for the fall. All of our summer internships, our REUs, et cetera, will be run remotely, as is being done for most sites. We're still holding at the hope, the possibility that they might be able to come together near the end of the summer to meet each other face to face, but that's still TBD. And last, thinking about all of these types of activities, our 20-meter telescope, which is our educational telescope and is very important under these times because it is a remotely run educational telescope, has been down as well due to a lot of those power outages I talked about earlier. The good news is, again, we're starting to work to slowly repair it, following safe practices, and we're hoping it will be operational soon, and that will allow us to increase our educational programs, as well as increase the training we'll be able to do for some of our summer students and summer interns. So that's kind of the big picture of what's going on, and I just wanted to end with the note that in spite of all of the concerns and all the worries going on with COVID-19, we still have fantastic science happening. I stole this image from recent observations taken either last night or the night before. So this is Astro 2009 XO. This is a little sneak peek at a bistatic Arecibo and GBT observations being done. Patrick Taylor at LPI is the PI of these observations. The image isn't fantastic. That's because the data is still coming in. So watch for a press release soon, hopefully from this group. And with that, I also want to mention quickly that we do have a survey coming out. It'll come through your email from same email that you got the notice about this. This is a survey for our GBT observers, just looking at ways we can improve the system and getting good feedback from our observers. So please watch your mailbox for that. So with that, I will go ahead and hand this over now to David Frayer. So meanwhile, I see a note about here as David's getting his screen set up that there was an announcement for DDT time proposals. Yes, that is still going on. This is focused primarily on the low frequency time proposals. So yes, that announcement is still out, and we encourage people to look at their science and put in a DDT proposal for low frequency time if they have it. So I think Dave is almost ready now to share his screen.
Yes, I can share. Is there anything else on the chat? There's a couple other.
No, I think all the questions were answered.
Okay. Is my screen visible?
Yes.
Okay, I'm just going to talk a little bit about the capabilities for spectroscopy in the 3mm band with the GBT. Of course, what makes observing at all possible at 3mm is the active surface of the telescope. In terms of, it's actually quite impressive when you look at the relative errors that we're able to maintain, about 200 to 30 microns over a 100-meter dish that is out in the open air, and that's a very accurate surface. And this makes the GBT the largest single dish in the world operating at 3mm. And I find this interesting, maybe others may not as much, but we've improved our ability to be able to push things up to 3mm. We had the active surface. In 2009, the 0 points of the actuators were set. But another aspect of it is what we call the Zernike gravity model, the residual gravity model that corrects things as a function of elevation. And this really didn't get updated and fixed until about 2010. And if you look at the plot in the upper right, way back in 2003, we had the finite element model, FEM model, for gravity, and you can see the relative effective aperture efficiency as a function of elevation wasn't very good. Then we applied a correction to that, and we can improve things at different elevations. Then from 2009, we fixed the locations of a lot of our actuators, and you see how the aperture efficiency effectively shot way up. But then after that, we fixed the gravity model, which is now relatively flat. So what this means is you can auto-OOF or set the surface at one elevation, and then you can go observe at another elevation without a loss of efficiency. And that's pretty important. ARGS 16, I call it, ARGS is a 16 element array. I'm going to refer to it as ARGS 16 because we hope to have an ARGS 144 version or some number larger than 16 in the future. It was commissioned in 2016, and this just shows some of the first data that came off that telescope. It operates from roughly about 75 to 116 gigahertz. I would like to say that we do have another receiver that's a 2-element, what we call the 4-millimeter receiver. It operates from 67 gigahertz up to about 92 and some change gigahertz. So we can go all the way down to the we can observe all the way from the oxygen lines at, the 65 gigahertz all the way up to the oxygen line at 118 gigahertz. So that's fully covered with the GBT. We did, and in good conditions, this is taken back a few years ago. We demonstrated that we could achieve the theoretical beamwidth ARGS. What I mean there is it has the same beam size as you would expect from extrapolating from a lower frequency. And we generally get about 1.2 lambda D beam sizes at high frequency with the GBT in good conditions. There's a memo out that we put together results from hundreds of observations of 4-millimeter and ARGS observations taken over several seasons, and it summarizes all the results in a GBT memo. I'm not going to go over all these parameters, except it demonstrates that we do have pretty good efficiencies. This is at 86 gigahertz, the aperture efficiencies as measured for Jupiter or on the moon, or all the, that's our forward efficiency. But anyway, these are actually pretty good numbers and pretty impressive for the size of the telescope. We have 2 large active ARGS programs. One is just getting started, and one is actually finishing up. One finishing up looking at gas in galaxies led by Andy Kelly. Just a picture here of IC342. This is CO 12 to 0. Most of that survey is looking at 13 CO, as well as the dense gas tracers of HCN and HCO+. And then we have another project that will starting to get ramped up. It had some observations which they published measuring some velocity fields in dense molecular cloud cores using N2H+. That's a good tracer because that freezes out. You can look down deep into the cores and measure the velocity structures of the cores that will end up forming stars. So that the initial project was successful. They got a large program approved to look at 108 cores. But that's just what we have now. We hope to build upon ARGS by building the ARGS 144 array. It's also, we've called it ARGS Plus, and so whatever number of elements we have, that will call it ARGS, hopefully it's 144. That's and so the idea there would operate over the same frequency range, but it would provide about a 10 times more mapping speed of ARGS to reach the same sensitivity levels that we currently do. And actually, sort of the amazing thing with the GBT, it's so big and sensitive. When you actually, if you're doing like 13 CO, you don't really need very much integration time if you're measuring very large scale structures on the sky. CO is everywhere, and we're currently limited by how fast we can frequency switch our LO. So we could potentially map much, much larger areas with ARGS 144. Most of the ARGS projects have looked at small regions on the sky. I think it's just the way the science community is biased a little bit by ALMO, just measuring clumps and cores and stuff. With this instrument, ARGS 144, you could map square degrees on the sky pretty efficiently. It would cost money. We do not have money. We've put in some proposals in the past. They've been rated fairly well scientifically. There's I would argue, a good scientific case for that, but In these times, financial times, it's always tough. You're always trying to argue. There's a lot of competition. So we do have a workshop plan. Larry Morgan is leading the organization of that. It's a little bit in the coming months or coming weeks, we're going to probably decide whether we're going to meet face to face or it will be done virtual. And so there's a web page for that that's linked off our Observatory event calendar. So if you go into the web page and look under events, you'll see it's on the calendar right now for September 22nd to 24th this year. And the goal there is basically to get the scientists together to discuss the ways we could take advantage of the potential new capabilities that Argos 144 would provide. I'd just like to remind people Argos 16, or our original Argos, was awarded basically for technology demonstration. It was not funded at the full level to build a general user instrument, although it was put together with the idea that we would use it obviously on the GBT, and we've taken advantage of that. But the integrated modules within Argos itself have performed remarkably well, and we'd like to build upon that success by building a larger scale instrument. So that's what I have. I'm gonna escape out on my display, and I'm not sure. So maybe Marty, somebody back from me, and I'm not sure if there are any questions or not. Whoops, I need to hit the stop share button. I'm gonna stop share.
Any questions for Dave? If not, we'll hand this off to Pedro then to start his screens up so he can talk to us about Lassi. Oh wait, we got one question here. Question is, Dave, if the LO switching is a limit, why not use the pause switch OTF?
Pause switch OTF. I'm not sure.
Why not do on the fly, position switching on the fly?
That's what we're doing. We're on the fly mapping with the position switching. Our LO can only switch by 0.4 seconds. And so that if you do a well-sampled map, you're going to end up, even if you take the most shallow maps possible that are well-sampled, you're going to have like 4 seconds per beam on the sky. You really only need 0.1 seconds on the sky. So all we need to do is, it would cost, in principle, $10,000, allow 2 LOs, $20,000 in hardware, and put 2 LOs and put a fast switch. Instead of restabilizing 1 LO, you would actually have 2 LOs and a quick switch. So we could do that now actually with some money. We'd probably Galen would probably choose the LOs that we just replaced on LO2 and replace LO1. We'd probably get 3 of them and replace LO3. But anyway, if we put a fast switch instead of trying to use 1 LO and then switch its frequency, we would have 2 LOs. They'd both be configured at their 2 different frequencies and just have a real fast switching in between. And you could map large areas on the sky very quickly.
Another question for you, Dave, which is, what are you estimating for the timescale for Argos 144?
It's dependent on when money is made available, to be honest. The farther we get away from the original Argos projects, technology does advance. So when we first wrote the proposal for it, was literally basically, we're going to do exact copies of like 9 copies of the original Argos. Now, over time, as time proceeds, the people that work with the different parts of Argos might have better ways and slightly improvements. So there'd be some development time, but literally that's a 3-year thing to get it built and up and going after we have, there's a commitment of funds. So 3 to 4 years in fairness.
And then finally, one more question for you, Dave, and we'll switch to Pedro. What is the fraction of time suitable for 3mm observations?
Yeah, thank you for asking that. I should have included that in this presentation. We have about it's with global warming, Tony would argue less, but the last time we make these measurements, we had about 2,000 hours where you'd have decent opacity per year. In practice, you have some windy days and stuff, and that may go down to 1,000 hours a year. of good time. Remarkably, in the winter conditions here, we have our median, or the mode of the water vapor distribution, is of only about 5 millimeters of water vapor, which is, I was always surprised when I saw that curve that Ron Madalena made, because that was very similar to what we observed at Owens Valley. Now, being out east, we have a much wetter tail to that distribution, so we have very wet days sometimes. But in the winter, when it's cold, we can have very dry conditions. So we've observed here a few nights of the year, we have, well, this is extreme, under 2 millimeters of water vapor. That would correspond to what you would get on Mauna Kea or the Alma site. We don't get that very often, but we do get that occasionally. But it's not unusual to have 5 millimeters of water vapor. And we can observe that 3 millimeters, for those who don't understand the scaling for millimeters of water vapor, up to about 10 millimeters of water vapor, you can get decent 3 millimeter spectroscopy data. So a good fraction of the time per year with the opacity is okay. So I would say 1,000 hours a year.
So with that, we'll go ahead and switch over to Pedro. So Pedro.
Yep. Can you see the slides?
Yes.
Yep. Okay. Thank you. Yep. Hello, I'm Pedro Salas, postdoc at the Green Bank Observatory. And today it's my pleasure to share with you some of the work we have been doing in developing this new instrument, the Laser Active Surface Scanning Instrument, or Lassi for short. During this project, I've been lucky enough to work with a wonderful group of people. Their names are here. And of course, that none of the things I'm going to show now would have been possible without their hard work. So thanks a lot to them. So I'm just going to tell you a bit what is Lassi. I'll show some examples of Lassi at work and finish with a brief summary of what I've shown. So what is Lassi? Well, it is this instrument which uses a commercial terrestrial laser scanner, a Leica scan station P40, which will be installed close to the telescope's focus to scan the primary reflector. Once we have scans of the primary reflector, we're going to use these scans. We're going to take the difference between them to measure the formations of the primary reflector. And then, thanks to the active surface, we will be able to correct for these deformations and conduct efficient high-frequency observations. This is where Lassi is installed. It's hanging from a beam on top of the receiver cabin. It's still not permanently installed, but this is where it will go. And from this position, hanging upside down, it can basically see the whole primary reflector. And that little cone above the scanner, which is not visible, it's basically because the scanner cannot see through its base. And that's a bit unfortunate because that precludes the view for the secondary reflector, but we do get the full primary reflector and more. What do we want to do with this instrument? Well, as I said before, we want to measure the formations of the primary reflector, and we want to measure them well and faster than out-of-focus holography. By well, I mean that we want to measure them accurately enough that we can actually improve the surface accuracy of the telescope and not leave large residuals behind. And for those of you who are not familiar with out-of-focus holography, I'm just going to say that that's the method currently in use to remove deformations from the primary reflector of the telescope. And we also want this instrument to be able to work during the day. So we have had the scanner for a little bit over a year. And even though it's not permanently installed yet, we have set it on the telescope using a temporary mount and conducted different experiments with it. Today, I'm just going to talk about two of these experiments. The first one, shown in the top diagram, what we have done is set the active surface to 0, that is, set the positions of the actuators to their 0 position, and then leave the active surface in this state and not modify it. And then with Lassi, we have scanned the primary reflector and done this continuously. In this particular case, we have done this for a period of roughly 24 hours. And the idea with this kind of experiment is to understand what external factors influence our ability to measure deformations using Lassi. The second kind of experiment we have done, shown here on the bottom, we start in the same way, setting the active surface to 0, then we do a scan, and then we try to imitate a thermal deformation by setting the active surface to reproduce a Zernike polynomial. And then we scan again. And then we repeat this the same cycle for a number of times using different polynomials. And the idea is to see if we can measure these polynomials well, and if there's any limitation, for example, in the amplitudes of the polynomials we can measure, or if some polynomials are harder than measured than others. So for the first type of experiment we have done, as I said before, we're going to be using differential measurements, so the difference between scans. So what we have done is take these scans and compute the difference between them using scans which are adjacent in time. Then we get these delta S maps, which I will call deformation maps, and this is how they look like. Here I'm showing 3 examples at different times. Shown on the top of each panel is the time of the scan, and the color scale basically is showing deviations above and below the surface of the telescope. Red means the data is above the plane of above the surface of the telescope, and blue below the surface of the telescope. On the leftmost scan, we see these ugly radial stripes, which originate at the location of the scanner. And these are not actual deformations of the telescope, but are artifacts in the scans. I will talk a bit about this on the next slide. But if we look at the second and third panels, we see that the surface looks just like noise, which is what we expect since we're just taking the difference between scans without modifying the surface. If we take the RMS over these deformation maps and plot this as a function of time, we get what's shown here on the top panel. And what we have done is compare this with the readings from different sensors installed across the telescope. On the second panel, we have in red and blue the wind speed as measured by anemometers in 2 of the weather stations installed on the telescope. On the third panel, we have in green the displacement, the relative displacement between the feed arm and the primary reflector as measured by a quadrant detector. On the fourth panel, we have in blue the readings from an accelerometer installed on the roof of the receiver cabin, so just below Lassi. And on the fifth panel, we have the temperature measured by 3 thermistors installed across the primary reflector. What I wanted to show with this plot is first that the RMS remains roughly constant on these deformation maps for a long period of time. That means that the instrument is stable enough over long periods of time. And the RMS is roughly 100 microns over the whole surface. This is not the actual surface RMS, I remind you, because we're taking the difference between scans. So this mainly the noise due to the scanner. In yellow are shown the 3 different scans I showed on the previous slide, these little yellow stars. And the scan which looked ugly with the radial stripes is the one here at the beginning. And we think that these radial stripes are due to the effect of the wind on the telescope. When the wind is above 4 meters per second, the displacement between the feed arm and the primary reflector is large enough that it introduces these radial stripes on the scans. And under those conditions, it's very unlikely that we would be able to measure deformations using Lassi. Luckily enough, this speed is also the wind speed used to schedule 3 millimeter observations. From the second kind of scans experiment we did, we also take the difference between scans, but in this case, we take a scan when the surface was deformed and one scan when the surface was zeroed, and then compute the deformation maps. And in this case, we expect that the deformation maps will show the deformations we input to the active surface. This is what we're showing here. And in this case, the surface does not look like noise anymore, but it actually looks like the deformations we were putting in. The color coding is the same, and we can clearly see the deformations that we input through the active surface. This is shown in a more quantitative way here in this plot, where we have on the top, on the y-axis, the measured amplitude of the deformations, and on the x-axis, the amplitude of the deformation input to the active surface. And here the red line shows a one-to-one relation. So if we had a perfect, if we were measuring the deformations perfectly, all of the circles would lie on top of this line. But of course there is some noise and there is some scatter around this red line. But overall, all the points seem to lie around it, which is very good. And on the bottom, we're showing the residuals between the input and the measured values. And we're very happy with these results because the mean of this of the residuals is -17 plus -49 microns, which overall is telling us that using Lassi, we should be able to correct for these deformations without leaving large residuals behind, so that the aperture, so that the surface error should be improved with respect to an uncalibrated surface. So as a summary, Lassi uses a terrestrial laser scanner to measure deformations of the primary reflector. We have been doing this using differential measurements. We're also investigating other options. And with the experiments we have been able to do so far, we see that we're able to measure deformations down to 55 microns when the wind speeds are lower than 4 meters per second. And thanks to the hard work of the team and the people at the observatory, we expect that Lassi will be operational during 2021. So thanks for your attention, and if there are any questions, I'll be happy to answer them.
So we've got one question for you, Pedro. Question is, what kind of targets do you use at the telescope surface?
Oh, that's one of the nice things about using a terrestrial laser scanner. You don't need a target. Basically, this scanner will just shoots a laser, and the laser bounces back from almost any kind of surface, and with that you get a distance without the need to have specific targets.
Okay, another question is, why not rotate the P40 mount so you can include the primary and the secondary surface?
That's something we're investigating at the moment. Unfortunately, we're investigating that, and that's something that, depending on the results, we would be very happy to in the future to actually have some means of measuring both the primary and the secondary.
Another question for you is, says, this looks exciting. Currently, OOF is still used?
Yep, we're still on the commissioning phase of Lassi, so we're not installed on the telescope, and we haven't finished ironing out all the details to make this a potential replacement for OOF.
Another question is, how much high frequency time would potentially be made available after Lassi is deployed?
I think that's a question for Jay. I don't have a number to give Herschel.
Jay, are you there and able to answer that question?
I'm here, but I'm not really able to answer that question yet. I mean, there are two aspects of it, and one is certainly reducing the amount of time that it's needed to correct for thermal deformations. To do an out-of-focus holography requires going to a strong source in the sky, and there's only a handful of those that are suitable at our frequencies. And then the other hope is that it will open up observing during the daytime, which could be a full factor of 2 in available usable hours at the highest frequencies. That's the potential.
Okay, another question is going back to an earlier one. Have you tried to measure the dish surface directly with the P40?
We haven't been able to do that directly yet, mainly because the scanner itself has large systematic errors. But a graduate student is coming this summer. I think I saw her among the participants, and part of her work will be to calibrate the systematic uncertainty so that we could then measure the surface directly and then get get direct measurements without having to use these difference maps.
Okay, are there any effects of weather conditions such as wind turbulence on the residuals that you've seen?
We haven't done a more detailed analysis of we see stuff like turbulence in the residuals, and the main effect we see from wind is from the relative displacement between the feed arm and the primary reflector, which introduces these radial stripes on the scans. But no, we haven't done a more detailed analysis on turbulence.
Okay, it's getting late, so I think at this point I will just thank everybody very much for your time on this. These talks will be posted up on our website within a couple of days if anybody would like to review them. And we are hoping to have another one of these talks in 2 to 3 weeks, so watch your emails. Again, thank you guys very much for your time. Bye-bye.